Good afternoon, ladies and gentlemen, and welcome to the plenary session for this second conference day. And I'm very pleased and honored to introduce you Professor Xanthippi Markenscoff, who's going to give a plenary lecture now, the title of which is The Dynamic Eshelby Problem, Nucleation and Growth of a Phase Change Defect Application to Deep Earthquakes.
Yes. I'm honored to be invited to give this keynote lecture here, and I thank you for this invitation. And I am really pleased to talk to the distinguished audience of this conference. The title of my talk is The Dynamic Eshelby Problem, the Eshelby ellipsoidal inclusion problem, the dynamic Eshelby inclusion problem, and how it can model the nucleation and growth of a phase change defect. By phase change means change in density and change in moduli, elastic moduli. This is a very general, it is applicable to any general phase change defect, but I will show specifically the application to deep earthquakes that I will explain what they are. Has been an open problem in geophysics for over a century, and now it can be solved as a phase change transformation under the high pressure. So what is a phase change defect? Here in this publication, PNAS 2016, shows a defect that is generated by shock pressures at 45 to 50 GPAs in boron carbide, and one wants to understand how such a defect is generated. At what loading can it grow? What shape will it take? What will be the expansion speeds? And what orientation it will take in the pre-stress field. So you want to know all of this, and all of these issues are addressed and obtained by the modeling that I will present to you. So you see that the shape is a flattened ellipsoid actually in these experiments, and there are very many experiments that obtain this defect. So such a defect are also the deep earthquakes that occur due to a phase transformation in the mantle transition zone. We have the surface earthquakes that are due to the friction of tectonic plates, like the San Andreas fault, and then there are no earthquakes, and then you go down to 500 to 700 kilometers, and then there are earthquakes generated from those depths, and these earthquakes are very large in energy, above 7.5 on the Richter scale, up to 9. And so in this zone, the geological material is metastable olivine, and it undergoes a phase transformation that involves a large change in density, about 10%, 5 to 10%, because under the high pressures it can go to another crystal structure where the atoms are closer to each other and transforms to these other minerals. So, the earthquakes, the faults that are produced and the radiation that is emitted is the same shear radiation as the one of the surface earthquakes. Now, the deviatoric stresses at these depths are very low and cannot explain how energy so large can be radiated from these earthquakes. On the other hand, the pressures are very high in this at this depth between 15 and 24 gigapascals. Now, there have been many hypotheses as of the mechanism of the deeper quakes over the year. The most intellectually appealing has been one of implosion. Implosion is a big volume collapse under the pressure. Brinkman, who got a Nobel Prize in Physics in '46 for the behavior of materials under high pressure, also was advocating this hypothesis. So what is wrong with this? So the change in density is 5 to 10%. So considering the high pressures there, the PDV energy is very, very large. But this hypothesis did not agree with what people were expecting that would be the radiation. If it was an implosion, they would expect the radiation of a pressure seismic source. But they are getting the radiation of a shear seismic source. So what is happening, so to speak? Is it phase transformation or not? Now, we have the problem of Randall, which is a sudden volume change under pressure. So isotropy, symmetry, the problem preserves symmetry, and the area of volume change, that is volume densification, volume reduction, expands spherically and emits pressure waves. What this literature altogether has failed to consider is the energy spent to move the boundary of a phase discontinuity. So if you consider the energy spent to move the boundary of phase discontinuity, then you have a series of symmetry breaking instabilities, and at a critical pressure, rather than having, there is another solution in which the under symmetry in isotropic material, under full material symmetry and loading symmetry, the area of reduced volume of the phase change will expand planarly because it will spend less energy to move a disk rather than a sphere, to expand a disk rather than a sphere. And so it will expand planarly and will emit the radiation of a shear source. Why it will do that? If you want to have a very large volume collapse, reduction, confined in a very thin pancake, in plain words, the atoms cannot overlap, so they will have to go to the side. This will create shear. The very large mean stress, that is tensile, is cancelled by the large compressive pre-stress, and the pancake will contain distortional energy to emit. Moreover, it will orient the eigenstrains this way so that there is no interaction energy with the pressure, so it will expand the pancake without the pressure confining the radiation. This is, all the community were concerned that the pressure will inhibit the radiation. No, because there will be no interaction energy of the antisymmetric stresses with the pressure. So indeed, then the phenomenon is that what are the deep earthquakes? Once they start, the material densifies, and at a critical pressure, it will start expanding on its own and at constant potential energy, and it will just grow. And so I will explain to you all these instabilities that is of phase transformations under high pressure. Now, the deformation fields that will be assumed are those of the dynamic Eshelby problem. The static Eshelby problem is solved by Eshelby in 1957. It is a paper with over 17,000 citations on Google Scholar, the most cited paper in solid mechanics in the 20th century, because of the properties that it has. So the dynamic Eshelby problem that we have solved is the self-similarly expanding ellipsoidal inclusion with a uniform transformation strain. And I will explain the unique properties of this problem. Then the energetics of the moving boundary of the region of phase change will be according to Nether's theorem of the calculus of variations in the variable domain. We have the J, L, and M integrals that express dissipation of energy in translation, infinitesimal translation, rotation, and scaling of the inhomogeneity position. So let me say a few things about the famous Eshelby thought experiment about how is the transformation strain obtained or quantified, modeled. So you have a material that is intact, and we take an element and we take it out of the material. So there is a hole where the element was taken out. We give to the element a strain, transformation strain, and it goes to a different configuration while it is unstressed. Now we want to put back this element into the hole. In order to put it back into the hole, we have to bring it to the untransformed configuration. For that, we would need to apply the stress minus the elastic constants times the transformation strain. These stresses can be produced by some imaginary body forces according to the equilibrium position equation. So that means that the transformation strain is an equivalent body force. If you want to, then you have to cancel this body force by applying the opposite one, and that will mean that you will have the Green's function for a point force, and the displacement field everywhere will be given as an integral of these derivatives of the Green's function. For uniform Markenscoff strain, it goes out, and Eshelby has shown that for the ellipsoid, the strain in the interior domain and consequently the stress are constant. So this is the famous Eshelby property for the ellipsoid. This Eshelby property physically is very important for the following reason. This eigenstrains, so the ellipsoid is a very general shape. It can be flattened ellipsoid, it can give a crack in a limit, it can give shear bands. All these defects that are here will have the same constant stress applied on it. So the ellipsoid will move as a whole. It will not disperse. The whole defect will move at every point. The defects will have the same stress applied on them, so the defect will move as a whole. Now, so the surface of the ellipsoid is a surface of discontinuity in components of the strain. The displacement is continuous, the traction is continuous, and for the problem of change in density or change in volume, we will have a given trace of the eigenstrains that would be large. Now, the self-similarly expanding ellipsoid will be, as we said, the eigenstrains will be a body force, and that body force is inside, this is the step function, and S's are the slowness 1 over the axis speeds of an ellipsoid. So with zero initial and radiation conditions. So we have solved this equation by different methods. One elegant way that was proposed or obtained by Robert Berridge for cracks was by the M elliptically expanding cracks by the M operator. The M operator, this is Navier operator. So if you apply the M operator, then you make the inhomogeneous equation homogeneous, and then you can solve the problem. This M operator induces slowness, an additional slowness surface to the P and S waves, and these are the M waves that have the ellipsoid surface as the degenerate wavefront. Now, the M waves are the ones that satisfy the Hadamard jump conditions on the expanding surface of the ellipsoid. L dot is the normal boundary velocity. The M waves, in particular limits, give the static Eshelby ellipsoidal solution. So this self-similar problem is indeed the dynamic generalization. And if the ellipsoid reduces to a crack for certain eigenstrains, then at the Rayleigh wave speed, they have Rayleigh waves. Now, if you have the constant stress property also, so in the dynamic problem, then you have also zero particle velocity in the interior. This is happening, as it's shown in the solution, because the M waves emitted from the boundary cancel in the interior domain the pressure and the shear waves. This is shown by the solution, but can be shown also without having the solution by analytical properties. This is a lacuna, is a topological property of hyperbolic PDEs, and that is zero particle velocity. Berridge described that as a moving region of absolute quiet. I should say that Robert Berridge obtained the Adams Prize in mathematics from Cambridge University, a very prestigious prize in 1971. In 1968, it was awarded to Penrose and to Hawkins. So this is very deep work for them waves, and so the lacunas were Petrovsky lacunas initially, and then Atiyah, Bott, and Garding have this paper. Sir Michael Atiyah is one of the major mathematicians of the previous century. So the lacuna is what allows the phenomenon to happen. Without the lacuna, it would not have been possible. So if you have the implosion, input energy, the pressure times the change in volume, PdV, let's say, where does the input energy go? There would be no kinetic energy inside. Then energy will be consumed in the nucleation expansion of the phase boundary. Let's say for cracks, moving at half the shear wave speed, 35% of the moving energy is lost in the crack expansion process, and the rest will radiate outside as seismic energy. So, how do we get the instabilities? The shape of the boundary we may call it an equilibrium shape, so it does not become the boundary a sickle of source of energy. From the dynamic J integral, you will get this expression, L dot the boundary velocity, and the jumps, the double brackets denote jumps. This is a well-known formula in phase transformation. So to have this zero, there are two possibilities. Either the quantity in the parentheses is zero, which is preserving the symmetry, or L dot is zero. So you have a flattened shape. You are going to have limiting in the limit L dot on the to go to zero on the flattened surfaces of the ellipsoid. So this is a possibility of symmetry breaking. So if you look at the M integral for which is the expansion under scaling, for the sphere it varies as the radius to the third power. For the penny shape, so this is a penny shape flattened ellipsoid, it goes as A squared. As A goes to zero, you spend less energy to nucleate a sphere. But as A goes to infinity, you spend less energy to grow large the pancake. So all the defects are pancake shaped at high pressure, including the deep earthquakes. Now, if you have then a pancake shape with a very large volume collapse, you do the asymptotics of the Eshelby problem, and so you would need to have very large volume collapse to go to infinity. The product of the eigenstrain times the ratio of the axis to go very small, very thin, to go to 0. So the product 0 times infinity goes to a constant. And then if you want the E33 strain not to be infinite, so you don't have overlapping, so you want the infinite terms to cancel each other in the eigenstrain, so that means you will produce unequal eigenstrain and shear stresses. So then the mean stress is large tension, but because the pressure pre-stress is also very large, then we don't have dilatational energy that explains the phenomenon, but we will have large distortional energy in the pancake. For here, still it is symmetric center of shear. Now, if you take the critical pressure for nucleation that I will mention in a minute, then you see, and you compare it with the mean stress that is tensile, and the critical pressure is compressive, for the geological material in the deep earthquakes, this is 0.3, so you have the pressure will overcome the tension, but if the Poisson's ratio is below 0.2, then the tension will overcome the pressure, so the material may break. And indeed, if there is the phenomenon, very famous, of failure waves, 1989, which has generated a large amount of research and was unexplained, why we get glass that has Poisson's ratio 0.19, that is just before this doesn't work very well, this 0.19 here, so we have tension that is left, and so we have in the glass so in the glass then you will have micro cracks opening in tension, and that can explain the phenomenon of the failure waves. Rod Clifton at Brown has worked on this for over 30 years, and he was very pleased to see my solution that he also believes solves many other problems that he has proposed in this area. So now successive instability will decompose the symmetric center of shear. So you need also to minimize the energy to expand the perimeter. We minimize the energy for the faces of the perimeter. So this, to minimize the interaction energy, it can decompose into two, what they call in double couple like that. So I will not say more about this. So let's go to the more important part of the phenomenon. What is the instability of nucleation and growth? If we have a small defect, a spherical, doesn't matter what radius actually, a spherical defect here that has a change in density and also change in bulk modulus, K to K star. If we look at then the integral, which is the invariance of potential energy under scaling, and this is also the derivative of the potential energy and the interaction energy, which Eshelby has extensively obtained, then we calculate the interaction energy, that is the interaction of the far field, that is a pressure here, with eigenstrains, two types, due to change in density and due to change in the moduli. and we will have this expression. If the pressure has the value that it makes the quantity in parentheses here 0, then you can have a delta A, an infinitesimal growth of the radius under constant potential energy. So at this this means any infinitesimally arbitrarily small inclusion can grow at constant potential energy if the loading has this critical value. And this value, we have obtained it also for the pancake geometry, and it is here. So let me give you some physical meaning. Some physical meaning of what is the vanishing of the M integral. Let's have a surface of discontinuity. Here is the inclusion with eigenstrains or different moduli. And then let's give an arbitrary velocity delta r dot to this point of the surface of discontinuity. And we want to see the flux of energy from the inclusion into the matrix, from the matrix into the inclusion, and the outward flux from the inclusion into the matrix. If these two are equal, then it is as if the interface does not exist. So it will expand at constant potential energy. This is the nucleation. So we just can use the Reynolds transport theorem for this volume S plus and for the volume S minus. And so we write the Reynolds transport theorem, and this is the change of the total energy, strain plus kinetic, and this is the one produced in the volume. But from the conservation of linear momentum multiplied by the velocity, we obtain this energy momentum relation here. So this volume integral can become a surface integral from the divergence theorem. So if we add these two together, we are going to get the change in the total energy of the system as function of the jumps across the interface. So this is exactly the expression of the M integral that you obtain formalistically from the calculus of variations. And so this says that if the pressure, that is the outward flux, the pressure here, I'm finishing about, this has low battery. So the flux will be the ambient pressure times the volume change. If this flux equals the energy influx from the matrix into the inclusion, then, and if it exceeds, the rest of it will radiate out. Actually, in the Eshelby thought experiment, when the element is put back in the inclusion, and that I showed you before, and it is left to relax, then energy is extracted from the matrix into the inclusion. So there will be this energy that is extracted from the matrix into the inclusion, but the applied loading will produce that. With this, we can obtain the radiated energies. I don't know what happened to it. I'll go to the end. No. I'm very close to the end. What happened? Yes, but let's move on. It moves. Yes. So this would be the input energy minus the energy to nucleate the pancake faces. And the rest is radiated out. With this calculation, we have I have so here I show for the deep earthquakes that have exactly the values of the materials, the geological materials, the phase, the change in density, and at this Oxcosh earthquake, magnitude 8.3 on the Richter scale at 609 kilometers. This is the critical pressure that is to generate the faces of the pancake with the radiuses that are estimated from the data that the seismologists have. This is the ambient pressure at those depths, and the difference of the two gives exactly energy that is amply explaining the large radiated energies of the deep earthquakes. And so actually, the question is also answered, why at higher depths you don't have earthquakes generation? Because at higher depths, according to the material constants, this peak critical may be more than the ambient pressure. So it can explain that. So another question, among all the orientation in space of the flattened ellipsoid, which one it will take? It will take the one that will minimize the interaction energy with the pre-stress field. And this is also explained in the initial slide that I showed you. So to minimize the interaction energy, I don't have time to show. The important thing is that the Eshelby ellipsoidal inclusion properties are also valid for a Newtonian fluid of the change of shape of a viscous ellipsoidal region embedded in a slowly deforming matrix having a different viscosity. So, in this paper of Bilby and Eshelby, so then the equations being stress invariant, the lacuna property is also valid for Newtonian fluids, and this connects solids and fluids in a very fundamental way in the phase transformations. And so I can finish here. I want to honor Eshelby and his student Mick Brown, also an FRS, wrote that Eshelby taught me once you had a mathematical result, the first job was to understand what it means. And I'm proud it was debated whether to show it, but the Miller Institute of Basic Science at Berkeley, that is like the Institute of Advanced Study at Princeton, had front page news. I was surprised to see it, that I was visiting Miller professor, the engineering professor solves deep earthquake history. So I think the geophysicists believe that. I have the paper published in the Journal of Geophysical Research, which has not published on the deep earthquakes since Lopov and Randall 1970. So this is an application to geophysics. I hope this conference is interested also in solid mechanics or in different applications across nature. Thank you very much for your attention.